Now we are going to see a number of problems where we can compute an unknown magnetic field by using Ampere's law. Let's remember Ampere's law. There was this integral expression of the magnetic field. I have said that this integral is actually quite hard to compute in most cases, and that's equal to mu0 times some current expression. So as a result, since it is quite hard to compute that expression in general, we cannot use this equation to solve any problem, right? That's not possible because the unknown is inside an integral, and it's actually hard to take an known integral, and it is much more difficult to evaluate an unknown integral, obviously. But there are some special problems where we can compute the left-hand side, this integral in here, by a single unknown. So there's usually this is some magnetic field strength. So as a result, I'm going to write an absolute value sign in here. So this strength multiplied with some kind of a length scale in here, this can be computed as like that by using a single unknown. And this only happens for problems with very high symmetry. So the symmetry should be so high that on the Amperian loop you should know the value of the magnetic field in terms of that single unknown, essentially. And of course, it's quite easy to find the right-hand side. By using this, we can evaluate the magnetic field, right? So the most important point that you should keep in mind is that the law is correct for all possible situations. There's no problem with this. However, you cannot use this to solve any problem. No, you can only solve problems with very high symmetry. And we are going to see that in that case, there are these three special problems that I have listed in here. The problems with cylindrical symmetry, solenoid type problems, and toroid type problems. So they have different kinds of symmetries actually. And so as a result, each problem have its own kind of magnetic field lines and magnetic field distributions. And so as a result, in each case, of course, we are going to choose a different Amperian loop. And for those cases, we are going to see that we can easily, by using the Ampere's law, we can easily compute the unknown magnetic field. So here I'm going to start with the simplest example. That's a cylindrical wire. The wire has zero thickness. And of course, it should be infinite in length. That is necessary. So it's an infinitely long wire. It's also straight. That's necessary for the symmetry argument. It doesn't matter whether it is thin or thick, but I'm going to start with the thin one. And the question is, well, there's this kind of a wire in here. We know the current on the wire, and we would like to find the magnetic field at a distance, at any point in space, actually. In that case, we have to use a parameter for the distance of the point from the wire. Again, let's just remember that for computing the distance of a point from the wire, we just draw a line perpendicular to the wire. And this r is that distance. It's not a radial distance from a point, it's a radial distance from a wire. Just keep this in mind. So as a result, this is a problem of cylindrical symmetry. Let's remember what the symmetry is again. There's a translation along the wire. There's a translation along the wire. That's a symmetry. That's a symmetry operation. So if I just translate this wire along that direction, the wire doesn't change, the current distribution doesn't change. So therefore, the magnetic field distribution around the wire does not change. There's also a rotation around the wire. So there's a rotation axis in here. In that case, this is the same as the wire. So rotations around this axis does not change the wire. So therefore, the magnetic field also does not change. So as a result, with these kind of symmetries, we can say something about the values of the magnetic field at different points in space. Okay, so since these problems are necessarily three-dimensional, it is always hard to draw them, hard to discuss about these kind of things. So as a result, sometimes I'm going to try to draw these kind of three-dimensional looking pictures, but when I'm doing the discussion, I'm going to always choose this one of these particular views. So sometimes the side view is nice. You're just looking at this picture from a side. And sometimes this front view is also nice. So I'll try to describe everything in here. So I'm just going to pick a point in here. So I'm going to use the yellow color for these points. So I know that at this point, for example, there's a magnetic field in here like that. So at that point, for example, on the side view, that point would be this point. And the direction of the magnetic field in that case, on that diagram, would be into the screen, right? In the case of front view, that point would look like that. In that case, the magnetic field would look like this. Okay. How do we decide on the direction like that? Let me talk about this a little bit later. But first, let's just say something about the symmetry, right? So one of the symmetries was the translational symmetry. So as a result, if I move along this, if I translate this point in the direction of the wire, then therefore in the new points that I reach by this translation operation, the magnetic field should be the same. So therefore on this diagram, for example, at that point, which is obtained by translating this point along that direction, the magnetic field should be the same. As a vector, it should be the same. So therefore, on the side view, it's going to look like that. So this is at this point, for example, we should have the same magnetic field. So let me draw this again because it didn't look that symmetric. So in any case, in here, the distance of these 2 points is basically the same. All right. So how does it look like in the front view? Well, in the front view, I cannot distinguish these 2 points. They are going to look the same. So therefore, the arrow that I draw for the magnetic field would be the same. All right. So as a result, this is one implication of the symmetry. So I can clearly show this on the side view, but not in the front view. The other one is the rotational symmetry. So if I rotate the wire around itself like that, so as a result, this point will go somewhere else. Where does it go? For example, in here, it just goes like that. It's hard to show it like that in here. If I rotate 180 degrees, and I am going to get this point, and I'm going to get that other point. In any case, since it's usually hard to draw these things, instead of drawing that, we usually draw the magnetic field line. So in that case, the magnetic field line is a circle. How does that appear on the side view? Well, on the side view, I cannot show all the vectors in here, but at least when I rotate this point by 180 degrees, I reach to that point in here, in which case the magnetic field should be pointing towards me. Again, in here, let me show the distance. That's the distance r. Now I can show the same thing on this front view. In that case, if I rotate the point by 180 degrees, I get to reach to that point. In that case, the magnetic field would be like that, right? It should have the same magnitude as this one, but it should have an opposite direction. So therefore, this is a difference vector. It's actually minus b. But in any case, we're not talking about these vectors in here. What happens if I rotate that point by 90 degrees? So in that case, I'm going to reach to this point. And if I rotate by 270 degrees, then I'm going to reach to that point. In any case, if I draw the magnetic field lines in that case, I clearly get a very clear circular shape in here. So The magnetic field line would look like that. So the symmetry argument basically tells you that the magnetic field at these different points have different directions, but whatever the directions, I can easily find them because they are basically tangent to that circle. And what else? It's just a circle with radius r. Let's just show it like that. Well, they have the same magnitude, right? So as a result, the magnitude of B, so I'm just going to show this without the absolute value signs. So without an arrow, of course, I'm basically talking about some magnitude, but I'm going to treat this as a component as well. So that means that in some cases, of course, it can also be negative. So just keep this in mind. But let's just say that this is magnitude in here. So magnitude is same at all points of the circle, of that circle in here. Right. I'm just going to just say that the B depends only on R. On the that radial distance. Right. So it's not just for this rotational symmetry in here. So as a result, if I have different points but at the same radial distance from the wire, in that case the magnetic field should have the same magnitude. That's also the case for these 2 points as well, because these 2 points have the same distance from the wire. And so therefore in all of these cases the magnetic field should have the same strength. All right, that's the implication of the symmetry. What is that useful for? Let me also say about something about this. So as a result, we're saying that, for example, the magnetic field in here at a different distance from the wire can have a different magnitude, right? So symmetry doesn't tell us anything about what that magnitude might be related to that magnitude. The symmetry doesn't give us any information about this. So we have to find the magnitudes by using a different argument in there. Right? Just keep this in mind. Another thing is about the direction. Okay, so all right, we basically know that the direction of the magnetic field is like that by using what we have learned from Biot-Savart law, right? So as a result, if the current in that picture, if the current is coming towards us, then the magnetic field should be like that. But let me redraw this thing in here. So as a result, this is the wire in here where the current is coming towards us. So there is a point in here. So as a result, Biot-Savart law tells us that the magnetic field in that case should be pointing directly towards left. But you might actually think about the other possibilities, like, I mean, could it be making an angle? Sorry about this. I have some difficulty in using this program. In any case, can it make an angle like that? So as a result, there might be some sort of an angle like that in here. So therefore, this magnetic field has a parallel component and a perpendicular component. So in that case, the magnetic field in here would be also making same kind of an angle, like that, for example. So as a result, in that case, for example, the magnetic field lines would be something like that, right? They will be these kind of shapes, the spirals in that case. Is this possible? Of course, Biot-Savart law doesn't tell us that the magnetic field actually has some component like that in here. But let me just say that in here, what prevents the magnetic field to have this kind of a radial component is actually the Gauss law for the magnetic field. If you just remember this, the Gauss law for the magnetic field basically tells us that this flux integral over a closed surface should be equal to 0. That's equivalent to saying that there are no magnetic monopoles. But if the magnetic field in this situation, for example, had a radial component, radially outward component, for example, in that case, that would imply that some magnetic field lines will always start from the wire itself. So therefore, there are these magnetic charges, actually the magnetic north pole distributed on the wire. But we know that this is not the case. So as a result, when we are applying this rule, we can easily see that there is no radial component in here. Okay, that's also a possibility that the magnetic field might have a component parallel to the wire. That's also a possibility. But in any case, we know from some other properties of the magnetic field that this is not the case. Okay, so as a result, let me summarize. Of course, when we are using Ampere's law, we cannot pretend that we don't know Biot-Savart law. At least Biot-Savart law gives us a clear indication of the direction in here. So as a result, if I just consider a point at a distance r, I know that definitely the magnetic field in here is pointing directly towards left. And so as a result, if I draw this circle in here with radius r, where the center of the circle is at the axis, in that case, at all points on that circle, I know the magnetic field has the same magnitude. Right? Let's just write this as a comment because that's important. So B is same. Again, not the direction. Vector is not the same at all points, but its magnitude is the same. Yeah, same on all points on this field line, which is a circle. Okay, so the trick is, of course, to choose the Amperian loop to be the same circle. We just choose the Amperian loop like that, and also choose the direction on the Amperian loop to be the same as the magnetic field. Right. So in that case, I just consider some line element in here. So let's say it like that. So I just pick a line element in here. So therefore it has a vector dl. I know that at that point the magnetic field is also in the same direction. So that's the direction of the magnetic field. Now I just draw this vector a little bit longer, but that just for I did this for clarity. Right? I need to compute b dot dl as the dot product. And I would like to integrate this. So as a result, I'm also writing down the integral in here. But you can see that this is a dot product. So therefore, this is equal to the product of the magnitude of the magnetic field, magnitude of the length element, and the cosine of the angle between them. But since these are parallel, the angle is 0. As I said, in most of the situations, this angle is either 0 or 180 degrees. So therefore, this cosine factor is either +1 or -1. So in that case, it's +1. So therefore, this is equal to BDL. Right, that's the first step in the evaluation of that integral. So let me also put this O sign in here because I'm integrating over a closed curve. So that's the first step, that we just express the dot product as the product of the magnitudes. Right, that's important because the magnetic field is not constant on the Amperian loop. The vector changes because its direction changes. But the magnitude of the magnetic field, this is constant. So since it's a constant, I can take it out of the integral. This is a nice thing that you have learned in calculus. So if there is a constant that you see inside an integral, you can take it out. So that's the second step. So In the first step, I just converted the dot product into the product of the magnitudes. In the second step, I just took the constant thing out. And what is left is some kind of a expression that it's a symbolic expression actually. It just is a prescription that tells me that I have a curve in here. I have to divide this curve into small segments, and dl is the length of that segment. And I have to sum over that length. Basically, this is geometrically the total length of the Amperian loop. Right. So that's the symmetry argument. So as a result, in this case, for example, I know what this thing is. That's 2 pi r. And I don't know what the strength of the magnetic field here is, but I have done what I have promised. So I had a complicated integral in here, but I expressed this complicated integral in terms of a single unknown in here. So since I can compute the right-hand side easily, I can evaluate that integral. Right? Let's just repeat the argument. So as a result, for this case, therefore, b dot dl integral, we just start with the Ampere's law. That's the official version. So as a result, in the first step, I just convert the integral into an integral over the magnitudes. And then in the second step, I just take the magnetic field out. And in the third step, I just recognize that this is basically the circumference of the Amperian loop. On the right-hand side, well, everything is easy in that case. Let's just remember, I just have a single wire in here that crosses the enclosed surface. So therefore, it's the current that passes over this thing. It's just the same expression again and again. So this then tells us that the magnetic field is equal to mu0 I divided by 2 pi r. So in all problems of cylindrical symmetry, we have this property that, let me just say it like that. The magnetic field lines are always circles, coaxial with the axis of the symmetry of the problem. We always choose the Amperian loops as coincident with these magnetic field lines. So as a result, in all of these problems, the left-hand side in here, the b dot dl integral is going to be the same. Only the right-hand side of that equation changes. So it's the computation of the enclosed current changes in problems, different problems with cylindrical symmetry. And so as a result, this is the part that that's going to be different. But the left-hand side is going to be the same. So as a result, at least for this infinite thin wire, it is quite easy to derive this expression. So the left-hand side has a very nice geometrical meaning. We can do that easily. The right-hand side can be computed easily. So as a result, it is quite easy to write down that expression in here. So if you remember, we have just evaluated some complicated integral to do this by using Biot-Savart law. But by using Ampere's law, this is a very trivial result.